Hello everyone, my name is Olga Garcia and I'm a second year PhD student at the Institute of Astronomy and at the Kavli Institute for Cosmology at the University of Cambridge. And today I will be talking about some recent work on constraining mixed dark matter models using high-redshift Lyman-α forest data supervised by Pete Erschig and by Martin Hennel. Let's start with some background. So the standard model of cosmology, lambda-CDM, describes a universe dominated by a cosmological constant that we interpret as dark energy, to less extent by cold dark matter, and to only 5% by baryonic matter. Now, this model has been incredibly successful at describing with great precision the largest scales with cosmic microwave background measurements at high redshifts as given by WMAP, Planck, or more recently ACT, down to low redshifts with the large-scale structure observed by the Sloan Digital Sky Survey or DESI, for example. However, on scales of dwarf galaxies or so, historically, this model has faced some problems, which are the so well-known missing satellites, cusp core, and too big to fail problem. And more recently, the amplitude of matter clustering has given rise to the S8 tension due to the disagreement in the inferred S8 value between primary, CMB anisotropies and that inferred from low redshift probes such as weak gravitational lensing or galaxy clustering. Now, the missing satellites problem has nowadays been largely resolved through the incorporations of baryons in high enough resolution simulations, so it is natural that cosmologists ask whether all these challenges can be solved through baryonic physics or whether alternative dark matter models could do the job. And this is further motivated by the fact that after a decade with ongoing experiments aimed at detecting either of the two most popular cold dark matter candidates, actions or WIMPs, no success has been achieved so far. So, already in the 80s, a form of dark matter called warm dark matter, corresponding to a particle that is produced thermally and that has a mass in the kiloelectron-volt range, was introduced. And in such a cosmology, clustering will proceed differently. And I am showing you this using the projected dark matter density field extracted from some of the hydrodynamical simulations that I use in my work and that I will be explaining into more detail later for a cold dark matter cosmology on the left and for a warm dark matter cosmology with a 1 kiloelectron-volt thermal relic on the right. And what we can observe is that the warmer cosmology shows a smoother filamentary structure. But to quantify this degree of clustering in cosmology, what we use is the matter power spectrum. So in this slide, I am showing the dimensionless linear matter power spectrum on the y-axis. This quantity corresponds to the variance of the density fluctuations inside a logarithmic wave number being in k, where these k modes are shown on the x-axis with a corresponding inverse scale on the top x-axis. And what this plot tells us is that for cold dark matter cosmology, this variance, that is, the density fluctuations, increase when we move to the smaller scales, that is, to the higher k modes. This matter power spectrum is plotted at redshift 0, and by studying this late time structure growth, we can distinguish between different dark matter models. So apart from the already introduced warm dark matter, we also have hot dark matter. And both of these models have the common characteristic of the hypothetical dark matter particle having a non-negligible primordial velocity distribution at the time of the coupling. And what this means is that the particle is able to free stream from the gravitational perturbations, damping a structure formation below the free streaming scale. And what we can see is that for hot dark matter, shown in green for a 30 electron-volt thermal relic, this suppression occurs at non-trivial large scales, which is why this model was ruled out very early on. However, for warm dark matter, now shown in red for a 5.5 kiloelectron-volt model, this suppression occurs at the controversial scales that I mentioned earlier, which is why this model has received so much attention, and current analysis exclude thermal relics lighter than 5.8 kiloelectron volts, and pushing this limit higher requires even higher resolution data, which is the reason why interest on these hybrid dark matter models or mixed dark matter models that we use in this work has re-emerged. In these models, a fraction of dark matter is allowed to be warm, and I am showing you in blue for a 1 kiloelectron-volt thermal relic and a fraction of 0.16 how the imprint of the matter power spectrum would look like. In fact, what I am showing here in blue and red is the 2 sigma allowed models that I found when I fixed the lowest mass and the highest fraction in my analysis. This now shows in hatch blue the region of allowed models, with blue models in different line styles delineating this region that are also exactly drawn from this accepted region of models, whereas in gray now I show the rejected regions of models. And now in the rest of this presentation I will go about in explaining how do we actually find these constraints. So the first thing that we need to do is to describe the dark matter distribution in these warmer cosmologies, and for that we use gas or baryons because gas trace dark matter very well. And I am demonstrating you this again with a 2D slice of the hydro boxes that I run in my analysis for gas density field on the right versus dark matter particles only on the left. And what we can see is that gas at these scales is indeed tracing cold dark matter, and at these redshifts under consideration, that is after the epoch of reionization, so around redshift 5 and 4. Actually, what is happening at small scales is non-trivial, which is that the gas is erasing some of this small scale structure, and we can see that in fact this density field looks somehow more smooth than the one in the left-hand side for cold dark matter. We understand this effect physically, and it's called the pressure smoothing effect, and it's due to the gas reacting to the heat put on during reionization. What this means is that this gas effect is degenerate to the dark matter free streaming effect, and we will need to account for this in our simulations and properly marginalize over it. Now, most of this gas is made up of neutral hydrogen, which is why in the past studies have used the Lyman-α forest to constrain dark matter models. And now I'm going to show you the Lyman-α forest in action. That is a photon emitted from a high redshift quasar that travels through the intergalactic medium and encounters neutral hydrogen clouds along its way, possibly exciting this Lyman-α transition and therefore leaving the corresponding dip or the absorption line in the quasar spectra on top of the quasar continuum, giving rise to this forest of lines. To interpret the small scales proved by the Lyman-α forest and to model these complex gas effects, we need to use hydrodynamical simulations. In this work, in particular, we use the Sherwood relic suite of simulations that model the intergalactic medium during and after the epoch of reionization, assuming a fiducial UP background model. These simulations allow us to obtain synthetic Lyman-α forest spectra by extracting information contained within each pixel in a box along different lines of sight. And from this spectra, we can construct the flux distribution, which I am showing in the bottom right of this slide, for instance, for a cold dark matter cosmology in red versus a warmer 2 kV cosmology in orange. And what we can see is that the colder one exhibits sharper features that do not appear in the warmer cosmology. We previously mentioned this pressure smoothing effect, and at the simulation level, we account for this by running simulations with varying thermal history. In practice, we vary photoheating rates and end of reionization redshift that go into this U0 parameter shown in the slide, corresponding to the cumulative heat injected into the gas by some redshift. We also account with another degenerate effect to this pressure smoothing and dark matter free streaming effect, which is the Doppler broadening of the lines, which will also suppress small scales. And we do this using the T0 and gamma parameter, the first one corresponding to the gas temperature at mean density and gamma corresponding to the power law index in the temperature power law that the low overdensities of the intergalactic medium achieves after the epoch of reionization under the assumption of photoionization equilibrium. And lastly, we rescale the flux distribution such that the mean flux matches that from observations, and we do so using the effective optical depth parameter. Now, to extract any cosmology, we first need to characterize the fluctuations in the transmitted flux along the line of sight, for which we use the one-dimensional flux power spectrum. This quantity is shown in the y-axis in its dimensionless form, and in particular we show data from Mike and HIRES spectrographs from the Magellan and from the Keck telescope respectively, and also from the XQ100 survey observed by X-Shooter spectrograph. We further observe the signature that a thermal relic of 3 keV in dashed lines lives in the power spectrum, and importantly, this signature appears at increasing larger scales or lower K modes as we move to higher redshifts. So in principle, by using this higher redshift data, we can detect this signature easily. And the other important thing to consider is that we still would like to place stronger constraints. In order to do so, we need to be able to access the scales where heavier thermal relics leave an impact, and these are the lower K modes or the smaller scales, which depend on the resolution of our instruments. So, to compare with resolution of more familiar surveys, such as for instance BOSS, DESI, or X-Shooter, I am placing here in a vertical line the Kmax resolved by these instruments. And what we find is that the maximum Kmax in this particular figure is of 0.2, 0.1 seconds per kilometer by UVES and HIRES. In this work, instead, we use data from WERA 2019 using higher resolution data from HIRES and also from UVES spectrograph in the BLT. And the Kmax in this case is of 0.2 seconds per kilometer. What this means is that we're able to resolve small separations smaller by a factor of 2, and that we have flux power spectral measurements at 3 redshift pins, 4.2, 4.6, and 5.0. In particular, I'm also showing here the feed from a 2 kiloelectron-volt thermal relic, and this is the idea in this project now to compare the observed flux power spectra to those extracted from the simulations. And on the right-hand side, I am showing the ratio of some of these simulated models to cold dark matter, where in the left, I am only varying the mass, and on the right, I am only varying the fraction. And the point for the left is to see that the lighter the thermal relic, that is, the smaller the mass, the longer the free streaming scale, and so lower K modes are affected by the suppression. Whereas on the right-hand side, the higher is the fraction, the more enhanced is the suppression in this small scale regime. Now, these are only the dark matter parameters, but we also need to include all of these other parameters that I introduced earlier in the simulation slide, which means that we end up with a very high dimensional parameter space and a large number of simulated models that span this space. And so to carry out our Bayesian inference analysis, we need to be able to sample our likelihood in this parameter space in an efficient manner. And so we consider incorporating a neural network emulator at the likelihood level to speed up this parameter inference step. So in the left-hand side, I am showing the architecture for the emulator, where we have a set of input cosmological parameters, and we have the outputted flux power spectra at the K-bins at which we have available data. And on the right-hand side, I am showing the process in which we enhance the performance of this emulator, where in blue and in red, in lighter colors, I'm showing the 2 sigma region of the error that we found when we use only one fold versus when we use the commonly approach of K-cross-fold validation, that is, when we average across the predictions of 10 neural network emulators. And we are showing that within 2 sigma, the error on the emulation is less than half of a percentage. And once we are happy with this, we run our MCMC analysis using the Cobaya code, and now we are showing how the best fit flux power spectrum model looks like against the data at the 3 redshift pins. In particular, we show this for what we call the default model. In this model, we are using Gaussian priors on this T0 parameter that have been observationally informed from Guidewalk's work, and we also correct our simulations for numerical convergence using cold dark matter only simulation. And what we see is that this default model provides a very good fit to the data with a slightly larger residuals appearing in these higher K-bins or smaller scales. And at these smaller scales, we have contribution from metal lines and also from possibly underestimated noise systematics, which means that we need to check whether the systematic has been calculated precisely from the dataset. And so what we do is that we run another set of analysis varying the amount of information at these last 3 K-bins. But before explaining this different set of analysis, we first draw your attention to the left-hand side, where we are showing the 2D posterior in the fraction and in the inverse of the mass plane. We choose this parameter because we would like it to be the parameter to be bounded such that we recover cold dark matter at the origin. And what this plot shows us is that there is a strong degeneracy between the fraction and the inverse of the mass parameter, such that the data seems to prefer light thermal relics as long as they are not very abundant, or heavy thermal relics if the fraction is very large, recovering cold dark matter. This default model is shown in darker blue, but we also run 2 sets of analysis where we reduce the amount of information in the last 3 K-bins, first by imposing a K-max cut, such that in principle we can compare with previous datasets with poorer resolution. And secondly, we also add a noise parameter at the theory level, such that if this noise parameter is bigger than 0, this will indicate indeed that noise has been misunderestimated. In practice, we would expect in these two cases for the constraints in the fraction to get weaker because we are reducing the information on the K-bins that are sensitive to dark matter free streaming, which is what we observed in this plot. We further check that these constraints do not change noticeably, changing the thermal priors and also adding a thermally dependent resolution correction. And finally, we have another analysis that includes the highest degree of modeling to our best of our knowledges and accounts for patchy reionization and also for thermal priors that have been informed of the Thomson scattering optical depth derived by the cosmic microwave background as inferred by Planck. And this is this tau CMB parameter that appears on the slide. And what we found for these two main sets of analysis is that they are very consistent with each other, occurring within less than 5%. So to summarize, we have provided the strong constraints on these mixed dark matter models using Lyman-α forest with an unprecedented resolution. And these results indicate that the data allows for a thermal relic of 1 kiloelectron-volt as long as it contributes less than 16% of the total matter energy density of the universe. And the next step would be to check what are the implications for these allowed mixed dark matter models by the Lyman-α forest for the S8 tension. Thank you for your attention.